non-trivial result in this field, but at this, I hope that it will give you some exposure to the topic, and at the same time tell you something new in the field. So it's a new result. Okay, so as you can see, this is going to be what are called SLEkappa, these processes. So I should define that first. So SLEkappa stands for Schramm-Lohner evolutions. So these are some stochastic processes, and there is a parameter kappa, on which it is dependent on. For this talk, I will only assume kappa to vary. I will only allow kappa to vary from 0 and 4. Okay, and in this regime, when kappa is changing from 0 to 4, it's a fixed parameter in this interval. These are some random curves in upper half plane. So this is your upper half plane, and these random curves start at 0, and it will start growing in the upper half plane in a random way. Okay, so these are some family of random curves in upper half plane, and the way it is characterized, it is as follows. So the characterization is done via the conformal maps. So what you do, so for each time t, you look at the image of gamma on the interval 0t. So you look at the image and remove that thing from the upper half plane. Okay, so what you get is a simply connected domain. That simply connected domain, you can map it using some conformal map GT back to upper half plane. Okay, and you can also do that in a way that near infinity, GTG behaves like a linear function. Okay, so like an identity function. You can also do that. So you can, in fact, choose your conformal map GT such that it behaves like Z near infinity. Okay, so Riemann mapping theorem does allow you to do that. Okay. Now, the SLEkappa, or the Schramm-Lohner evolution kappa, is characterized so it's a curve gamma, so that if you obtain these conformal maps GT, then it will satisfy something called Lohner differential equation. And what is this differential equation? It is like this. It reads as follows. So d by dt of GTG is given by 2 divided by GTG minus something, root kappa times Brownian motion, something. But here what you do, you choose this to be Brownian motion, standard Brownian motion. Okay, so at this point, I'm not sure if everyone is familiar with Brownian motion, but I should just give one line about about its definition. So Brownian motion is a stochastic process which is continuous, and it has independent and stationary increments. Okay. So if you plug in root kappa times Brownian motion here, then this GTG is, so if GT is the solution to this differential equation, so that will be the characterizing property of SLEkappa of the curve gamma. Okay. Now, so there I'm putting a lot of details under the carpet, but this is what there is. The punchline of this story is that you characterize your curve gamma not by looking at the evolution of curve gamma, but you fix a z somewhere here, like that. And suppose you're living in a universe, so your observation universe is this. And as your curve grows, your observation universe itself is changing. And then you prescribe the evolution of how you see this particular Z in the changing model of changing universe. Okay, so instead of trying to describe the evolution of gamma directly, you describe the evolution of your observation of a fixed point as your universe is changing. So this is exactly the message. And if you do that, then you can describe the gamma in a much simpler way using this differential equation. Okay, this is called Lohner differential equation. Okay, so I hope at least to some extent the definition is clear. What are SLEkappa curves? Okay, so why are these curves very important? It turns out that these curves appear as a scaling limit of various statistical mechanics models.
Well, Atul, I think there's a question from the audience. Is that?
Yes, tell me.
Maybe not. Sorry for the interruption.
Okay, yeah, sure. I think it's Sivguru.
Yes.
Yeah, okay. Hi. Yes, tell me.
Yeah. So this is probably like a very basic question, but what happens to that curve under the conformal map? Where is it going to in the boundary?
No. Yes. So to a priori, the confirmed GT is only defined away from the curve.
Mm-hmm.
And it will, so if you approach, let's say, this point on a curve from this side at this side, different side, it will get mapped to two different points, depending on how you approach. So the tip will get mapped to a unique point. And that exactly will be the Brownian version.
Oh, thanks.
Yeah, but a priori it is defined away from the curve. Yeah. Okay, so why are these SLE processes important? And it is important because it appears as a scaling limit of various statistical mechanics model. And here are a few names, and I'm not going to define all of these models: percolation, icing model, loop erased random walk, self-avoiding random walk, and many, many more. So there are various statistical mechanics models in which you can find SLE as appearing as scaling limits. So just to convince you, let me just cover two examples. So let me consider the example of percolation exploration process. And this is as follows. So you consider hexagonal lattice in upper half plane like this. And suppose on this side you fix your hexagons are always colored white on this edge. On this edge, it is always colored black. And on the rest of remaining hexagon, what you do, you flip a coin with, let's say, P and 1 minus P probabilities, and you color it either gray or white. Okay. And if you choose P to be a particular value, something called the percolation exponent, the critical percolation parameter, then, okay, so before that, no matter how you color, so if you color the hexagons using this percolation experiment, you can always find a curve, this red curve that I show here, which has gray cells to its left, and to its right, it has white cells. And this process is called percolation exploration. So it's a interface between the gray cells and white cells. And if you pick your parameter P, the percolation parameter P, to be the critical one, again, I'm not going much in detail, one particular value of P, And then if you make the lattice size goes to 0, the size of this lattice goes to 0, then what you will see that this red curve will converge to SLE6. So again, this is one example where you see that SLE processes, Sham-Donner evolutions are naturally appearing. Okay. Let me
So
give.
Atul,
Yes.
was this proved by Smirnov? Who proved this? Scaling limit?
Yes, I think yes, Smirnov would be one name, and then so I think the best paper to read this proof is by Kamiya and Newman.
Okay.
So Smirnov did prove.
You mean Federico, right?
Kamiya, yes, yeah, Kamiya, yes.
Oh, thank you. Thank you.
Yeah. So Smirnov did prove it, but he actually, I mean, wrote a paper after which it was obvious how to prove it, but nobody wrote it very explicitly. And then Kamiya and Newman wrote it in a formal way. So the best way to read about this is this paper. Okay. So this percolation exploration does converge to SLE6. This is one example. Then let me consider another example, is SLE2. So this is loop erased random walk. Suppose you start at origin and you start moving randomly. You go to the nearing edge with equal probabilities. Let's say like this, like that. But whenever you form a loop, that's what I have represented in the red color. Whenever you form a loop, you erase that. And then you again keep on going. Again, whenever you form a loop, you erase that. Again, when you form a loop, you erase that. And then what you will get a simple curve like that, the red one, the black one. And if you consider that curve, and again take the lattice size goes to 0, then that will converge to SLE2. So this is another example where you would see SLE processes appearing as a scaling limit naturally. And here are some pictures just to capture your imagination. So as you vary your kappa, so kappa equals to half, 1, 2, 4. So when kappa equals to 0, the SLEkappa is just a straight line. But as you change your kappa, it starts becoming more and more deformed like this, more curvy like this. Okay, so this is how SLEkappa curves look in a graph. Okay, so the study of SLE Sham-Donner evolutions can be pursued in many directions. So you can study SLE directly as a process, so just study its properties, or you can study the convergence of various statistical mechanics model to SLE. So various discrete models converge to SLE. So you can study that problem. And you can also study connections of SLE with other random geometrical objects. And so as one of our senior colleague in this field, Stefan Rode, he likes to say that SLE is just a tip of the iceberg. So once you start studying SLE, there is a bundle of many random geometrical objects which are connected to these processes. And this area it constitutes a study of all such things. It's really a very big, dynamic, active research field. Okay. Okay, so this is kind of an introduction to what these processes are. Now, even though this is a big field, for this talk, I want to select just one particular topic, which I announced in the title, and talk about just that. So this is about the Welding homeomorphism. Okay, so I have defined SLE. Now I should also define the other buzzword, Welding homeomorphism. What are these things? Okay, so let me do that. So before defining the Welding homeomorphism of SLE, let me do it. Let me define it for a Jordan curve first. So for a Jordan curve, is my whole screen visible, Nishant?
Yes.
Till till here? Yes, okay.
No, wait. I think, so, right, it is visible. If I remove the bar, then it is visible.
That's exactly my problem was as well. Yeah, okay. So maybe I should, anyway. So the Welding homeomorphism of a Jordan, let me define it for Jordan curve first. So suppose you have a Jordan domain omega here. Then what you can do, you can find a conformal map F, which takes the inside of the unit disk here, inside the two inside of the omega. At the same time, you can also find a conformal map F star, which takes the outside of the curve, outside of this unit circle, to outside of the of omega. And it turns out that both of these F and F star, you can actually continuously extend it to the boundary. And using that, what it gives you is that it gives you a homeomorphism of the unit circle, which is defined as follows. So P and Q are mapped under these homeomorphisms if the image of P under F is same as image of Q under F star. Okay. So this homeomorphism is defined to be the Welding homeomorphism of this Jordan curve on the right. Okay. And what it is a way of encoding the Jordan curve in a conformally invariant way. That is to say that if you map your Jordan curve under some conformal map, then your homeomorphism will not change. And these Welding homeomorphisms are defined in a way that it is compatible with the conformal structure inside the Jordan domain and the outside of the domain. So this is exactly the point. So these Welding homeomorphisms are a way of encoding the conformal structure inside and outside of these domains. Okay. Now it turns out that this encoding is a very nice object, and depending on what problem you're looking at, it can make your life much easier. So you can address many problems about the curves using the Welding homeomorphism. And in many situations, it also characterizes the omega of the Jordan curve. For example, let me consider the case of quasi-symmetric Welding homeomorphisms. And it is as follows. The definition is as follows. So a homeomorphism phi is quasi-symmetric if you consider if for some m larger than 1, for any two sub-arcs of S1 with equal length, the image of those arcs under the map phi, the length of the image will be comparable. Phi I and phi j has comparable length. So in such cases, it turns out such homeomorphisms are called quasi-symmetric homeomorphisms, and in such cases, it turns out that the boundary of omega, this Jordan curve, is actually uniquely determined from this given homeomorphism. Okay, So in many cases, it actually also characterizes the Jordan curve. So it is a good encoding in many cases. Okay. So having said that, now let me go to.
Sorry, Atul, how do you recover the boundary of the domain from this phi? So you have a homeomorphism, let's say it's quasi-symmetric.
Yes.
I mean, I just want to understand how is it uniquely determined?
So there is a there is a unique domain, Jordan domain omega up to conformal transformation, okay, such that its Welding homeomorphism equals to phi. This is the uniqueness statement.
I see. Okay. So no, sorry, I misunderstood. I was thinking somehow to recover it back, but okay, yeah.
Yeah,
Thanks.
and construction is it is very deep. Yeah, this is a very non-trivial statement, but it is unique. So you can construct, and you can construct it uniquely. Okay. Okay, so that defines the Welding homeomorphism of Jordan curves. Now let me do the same for simple curves like what we see in SLE, in the definition of SLE. Now, when you have a curve like this, the role of inside and outside of the curve is played by left and right of that curve. So this is the corresponding variant of that. Now, in this case, when you map this curve by a conformal map G up onto upper half plane, what it will do is, you should imagine it like this. So it will zip so imagine there is a zip attached to this curve, and you are unzipping the curve onto here. So you unzip it flat. Imagine that process. I don't know if I'm explaining it well, but imagine it moving in this direction like that. Okay. So what the conformal map does is it will flatten this curve out. And again, if you consider this point, and if you approach it from left or right, you will get mapped to two different points here and here. So let me call that P. Then P is mapped to X minus and X plus. And the tip will get mapped to a unique point. And you can choose it to be 0. Okay, so I hope that is clear. And the Welding homeomorphism in this case is, you can actually define the correspondence X plus mapped to minus of X minus. Okay, so in the curve, when gamma is a simple curve, the Welding homeomorphism is defined by this correspondence, X plus mapping to X minus of X minus. Okay.
Atul, sorry, I have a question.
Yes.
This is Venki here.
Yes. Yeah. Hi, Venki.
So the thing is, what about the curve? Like what kind of curves do you allow? For instance, can you have like a spiral that spirals to a point?
You can do that. Yes. Yes.
Oh, okay.
So you mean like this?
Yes, but then your capital T will probably be infinity, but that's okay.
No, as long as you are spiraling to a single point, then it is okay. But if you spiral to a big domain, then you are in a problem. Because this single point is still visible from it is very visible in a complicated way, but it is still visible from the infinity.
Okay. So such type of curves are also okay.
Yes, yeah, spiraling to a single point is still also okay. Yeah.
Okay, thanks.
Yeah.
So I had another question, Atul.
Yes.
When you said left and right, you showed previous examples where the curve was really undulating, right? So what you would do is like take a small ball and look at the connected components, and then see which of them go to like the minus infinity of the x-axis and plus infinity x-axis. Is that how you decide which is left and right?
So right now I'm looking at simple curves only.
But yeah, but even simple curves, they could really sort of wind pretty crazily, right?
Yes, yes, but as long as it does not touch itself, you are okay. Yeah.
Okay.
It can come very close to itself, but you don't allow it to be touching itself.
Yeah, it is basically up to, so you just look at accessible points, whichever, how many ever equivalence classes there will be. So here every point except the tip is accessible from, there are two equivalence classes. That's why you get x minus and x plus.
Exactly. Yeah, exactly. Yeah. Yeah, so in the case of a curve, simple curve, you can obtain the Welding homeomorphism like this. Now, so now we know that SLEkappa curves are simple for the range of kappa between 0 and 4. Then you can actually construct, you can take phi kappa to be the Welding homeomorphism of SLEkappa. Okay, and the question that I ask is phi kappa, the Welding homeomorphism, continuous in kappa? And our motivation to ask this question is to study a well-known open problem in this area, which asks, is the curve gamma kappa continuous in kappa? And there are various underlying motivations to ask this question. And so you know that gamma kappa is appearing as scaling limits of various statistical mechanics models. And in the discrete setting, you also expect these various statistical mechanics model to vary continuously when you change the certain parameter in that model. So there are many motivations that one expects that these gamma kappa should be continuous in the kappa parameter. But at the same time, this is a very difficult problem, extremely hard to solve. And the main reason behind that is that continuity of the map, which takes the Brownian motion and maps it to gamma, is very poorly understood. So when you change your kappa, you know that this guy is changing continuously. But this does not imply that the corresponding gamma changes continuously, because this map, the continuity of this map is very poorly understood. So that's one of the reasons that this problem is extremely hard to solve. Okay, so our hope is to use this idea of using welding homeomorphisms in order to address this problem. And our hope is as follows. So we hope that the continuity of the welding homeomorphism should imply the continuity of gamma kappa in kappa. And why is that? So we have further motivations to support that. And suppose if you were in the case that phi kappa is quasi-symmetric, then you know that quasi-symmetric welding homeomorphisms characterize the curve uniquely. Then you can expect that if you change your welding homeomorphism continuously, then the corresponding curves should also change continuously. You can at least hope that. But there is a bad news that phi kappa are not quasi-symmetric at all. And this has to do with the fact that Brownian motion is not 1/2 order. So this is another result. And it turns out that welding homeomorphisms of SLEkappa are not quasi-symmetric. Okay, but there is a good news, and the good news is this, that these curves are conformally removable. Okay, so I should make sure that everyone knows this definition, what conformally removable mean. So let me define it.
So Atul, can I ask a question?
Yes.
So even if the curve gamma corresponding to this welding homeomorphism is not unique, but is there something that you can say about the family of curves that you get, or there's absolutely
no? When you don't have quasi-symmetric, it is very difficult to handle.
I see.
You get very less information, from that. Yeah.
Please go ahead.
There are some generalizations of quasi-symmetric conditions, but even use phi kappas also do not satisfy that. So it's a tricky one. Yeah. Okay, so the good news is that these are conformally removable, and let me define what this mean. It means, so the definition of conformally removable is as follows. So you have a set, suppose you have a compact set K, it is called conformally removable if you consider any open set U which contains K and any homeomorphism U to V such that F is conformal away from K, then automatically F is also conformal everywhere. So if a case has this property, if a compact set K has this property, then it is called conformally removable. And here is an example. I think we all study in our complex analysis course. Single points are always conformally removable, right? If you can continuously extend your holomorphic map, then continuous extension is also holomorphic, right? And it turns out that the concept of conformal removability is important because of this fact, this correspondence, that your curve gamma is characterized by your welding homeomorphism phi, if and only if gamma is conformally removable. Okay. Again, up to you characterized up to Mobius transformations.
Sorry, Atul, I'm a little unclear about this definition. So set is conformally removable if, so what in this definition, what is the conclusion? The conclusion is that which set is going to be conformally removable? K, I see. Okay, all right.
Yeah,
okay.
I should have written something. Yeah.
So, and then also, I didn't understand the motivation that you mentioned for the question that you want continuity of phi kappa in kappa. So you mentioned that with the motivation is something related to the continuity, like the corresponding continuity of the gamma K, right?
Yes.
But gamma K, we know that there are special like values of kappa at which the behavior of gamma K significantly changes. Like
yes, but it also changes continuously. Yeah, there's no, I don't think there is a jump. It changes continuously. Yeah, it should change continuously.
Okay, I see. Okay, thanks.
Yeah. Okay, so yeah, so the concept of conformal removability is important because of this correspondence. And there is also a famous theorem by Jones and Smirnov, which says that if you consider a Jordan domain, which is a holder domain, and by holder, I mean that if you consider the uniformizing map, then this is holder on D closure everywhere. if that is true, then the boundary of that domain is conformally removable. The boundary of holder domains are always removable. Okay, and there's another theorem which is by Rode and Schramm. It says that if the complement of the SLEkappa, when kappa is less than 4, is holder. So that implies that gamma kappa is removable. And what this implies in turn is that the Welding homeomorphism contains all the information about the curve gamma. So this is why we expect that if I prove that if I can prove that the continuity of these Welding homeomorphisms, then I should expect that would imply that the gamma kappa is also continuous in kappa. Okay, so this is again, there are a lot of technical details hidden, but at this point, this is only an idea, but it is an idea worth pursuing. Okay, so for this talk, let me be content. Let me address the first problem itself, asking that is phi kappa continuous in kappa? Are the Welding homeomorphisms continuous? And this is what we proved, and this is a result that it says that there is indeed a random field psi kappa x, where kappa is taking value from 0 to 4 and x is 0 to infinity, says that psi is jointly continuous. For each kappa, it is a homeomorphism, and it actually matches with the Welding homeomorphism of phi, the phi kappa of SLEkappa. Okay, so that indeed proves, this implies that phi kappa is indeed continuous. Okay, to be precise, it says that it has a continuous modifications. Those who are familiar with stochastic terminologies, yeah, the main message is that yes, it is indeed true that it is continuous. But yeah, again, so from here we would like to go all the way to gamma kappa, in continuity of gamma kappa in kappa, but that requires more work. Okay, so
for all k is outside the probability statement, or is it inside?
Yes, no, it is outside. In this case, it is inside, but here it is outside. So it is so psi is a continuous modification of phi kappa.
Okay.
Yeah. Okay, so that's the statement of our result. Now, in order to prove this, you can actually you can do you can take couple of strategies. The first one is using what are called Bessel processes, and there is another strategy which is something called Liouville quantum gravity, and the second approach is it's like using a missile to kill a bird. So I would not be telling you, I would not go at all to addressing this approach. Maybe if I get time in the end, I can say a few words. But there is a simpler approach which is called using Bessel processes, and let me give you a few remarks in that approach. So how can was there a question? No, okay. So how does Bessel processes come in picture? But even before that, let me define. I'm assuming not everyone is familiar with Bessel processes. So let me define that. So what is a Bessel process? A Bessel process of dimension, so a delta dimensional Bessel process started at x greater than 0 is a solution to this equation, this ordinary differential equation. Okay, starting at x greater than 0. And it will look something like this. It will, so there is a drift. So whenever xt is small to close to 0, there is a push in the Brownian motion term. Now it turns out that, so if you plot your Bessel process, it will look something like this. And what can happen that it can come and hit 0, or it can stay positive for all time. Both can happen. And that really depends on your delta, what delta you choose. So depending on what delta you choose, it can come and hit 0 at infinite time, or it cannot do that. And it turns out that when you pick your delta to be less than 2, then you do hit do hit 0 infinite time. So this Tx is the first time where it hits 0. Okay. Now, before telling you the details of what is the relation of this between this and welding homeomorphism, let me ask a related question. Is Tx continuous in X? This process of hitting times, and again, I'm assuming, let's say delta is less than 2, so that we know that this is finite. Is this continuous in the X parameter? So let me consider one example, delta equals to 1. In that case, what you prove, so look at the equation. If your delta is 1, there is no drift term. This is 0. Right? So then you just get xt to be x plus bt. In that case, what it implies that your hitting time is the first hitting time of Brownian motion on level minus x. And these are first passage times. So I taught this in my class, last class. So I hope the students are familiar with that. And if you consider this process T for Brownian motion in the variable x, it is not at all continuous. It is actually a Levy process. And it has jumps. So it is not true that this process is always continuous in the x parameter. Okay. But what we prove is this, that suppose your delta is less than equal to 0, your dimension parameter is less than equal to 0, then it is true. Then your Tx process is continuous. And in fact, this process, if you also account for the dependence of Tx on the dimension delta, then it is actually jointly continuous as long as you have delta less than equal to 0. Okay. And this in particular, I claim that this implies the continuity of welding homeomorphism. And why is that? The reason is as follows. So remember, your SLEkappa was something like this. Right? And your GT was mapping it to upper half plane. Now, this dynamics of GT as T times T varies, you can actually look at the inverse map FT. And so you can evolve your upper half plane H in a certain way so that you transform your upper half plane into this domain, into H minus gamma. So what you do is as follows. So suppose you start with upper half plane, and I start moving each of my point in a certain way, in a particular evolution. And if you choose your evolution in a particular way, what I'm claiming is that you can transform the upper half plane into the complement of SLE curve, into this complement domain. And that evolution is exactly given by this equation. So each point Z in the upper half plane, you let it evolve under this dynamics, under this equation. Then each point Z will go to something, some H1 of Z, right? So under that flow, the upper half plane will get transformed exactly into this complement domain, the complement of gamma. Now, if you look at the flow of this thing, so instead of letting the upper half plane flow under this dynamics, if you look at the flow of real points, you notice that this is exactly the flow of Bessel processes. So remember, 2 by, so the Bessel processes also had 1 by something in the drift. So what I'm claiming is that flow on the flow of this, the flow which gives you SLE in the end behaves on the real line actually as Bessel processes. And that, using that fact, it actually follows that if you choose Y and X here, which are image of each other under the Welding homeomorphism, that happens if and only if the Bessel processes started at X and Bessel processes started at Y, they both hit 0 at the same time. Okay, so there is a lot of detail that I'm like sweeping under the carpet, but the main message is exactly this: is that to construct the SLE, the complement of SLE curve, the domain which is the complement of SLE, you can evolve your upper half plane under this flow, and this flow actually behaves like Bessel processes on the real line. Okay, and that implies that
you have
yes.
about 5 minutes more.
Yes, yeah. And that implies that X and Y are image of each other under the Welding homeomorphisms, if and only if you start your Bessel processes at X and Y, they both hit 0 at the same time. And this is exactly the connection of Welding homeomorphism phi with the process dx. So if you know the continuity of the process T, then from there you can actually very easily conclude that continuity of the Welding homeomorphism. Okay. So I wanted to say a few words about the proof, but I guess that will require more time. So let me not say anything about the proof.
You can take a few minutes. That's not a problem.
No, I think it will. Yeah, it will be. It will be it will take more than that. So let me avoid saying anything about the proof. But if you guys are interested, we can discuss that in person. Okay, so I guess I will stop here. Okay.
So let us thank Atul for the wonderful talk that he has given. So I open the floor for questions.
Maybe in the question you can ask about the proof, and then I'm forced to tell you all the details.
This is called question fixing, Atul.
Yeah.
Okay, since you insist, why don't you tell us about the little?
Okay. Yeah, sure. Okay, let me do that. Actually, so proving the left continuity of Tx is very easy. I mean, you need to use some basic facts about ordinary differential equations. But proving the right continuity is slightly trickier. So what it says is that suppose I have x here, then my process Tx is like this. And suppose I approach my x from the top, y, then the hitting time of that should be close to Tx, something like that. Now, you can actually prove that if you look at this value at time Tx here, so this distance will be if small, if y minus x is small. That you can also prove pretty easily using, again, normal facts, usual facts from ordinary differential equation theory. Now, it turns out that the key thing to prove is to exactly prove that suppose you start your process at some small height, then you actually hit zero in very quickly. But you also want to show that that happens uniformly over for all Bt minus Bs. This happens. So this, as your x varies, Tx will vary over somewhere here. It can change anywhere. So you want to prove this fact that whenever you start small, then you hit zero very quickly. You have to do that over all time scales as your Tx varies over. So that this is what it is. So it's if Tx is the hitting time for Bt minus Bs, this Brownian motion. So then you prove that this thing is zero for all S. And again, in order to do that, what one does is as follows. So suppose I start at small x, then I construct an IID sequence like this. So you let your Bessel process run till it hits zero. Now at that time, you again go to the level x and you again repeat that thing. And using this, you can construct in IID sequence of random variables. And you want to run this iteration till the time you cover the whole time interval 0 to t. Now, it also turns out that this IID6, so this gives you a random walk actually. And this random walk has, so in the particular case of delta equals to 0, this has infinite mean.
So the random walk is just, so what is the random walk here?
The random walk is these times. So,
I see.
These times.
Okay.
And you want to run your random walk till you cross the level t. So it's like covering the interval 0 to t using some random intervals. And it turns out that this random walk, because it is zero mean, it actually grows like n log n. So usually you have Sn by n goes to the expected value, but expected value is infinite. So it actually goes like n log n. And from there, you can estimate how many iterations you need to take in order to cross the level T. And this will be slightly better than, because of this log n factor, you get something better than what you expect in the normal situation. Okay, and having that, you can actually also do some further computation to make sure that each of these individual steps is also small. And so that essentially gives you that this TF-SX is small whenever X is small for all S. Okay, so I'm again hiding a lot of details under the carpet, but the main message here is this log n factor, that if this log n factor was not there, our proof will break out. Our proof will break, so it will not work. So yeah, so this is kind of the idea. This covering argument is the main idea behind the proof, that you cover your interval using a random walk with infinite mean random walk, which has a log n factor. Okay, I'm sure I did not explain it very well, but I think that will require more time. But again, if you are interested, we can talk personally.
Other questions from the audience? All right, so there were plenty during the talk. So let's thank Atul for the wonderful talk again.
Thank you for listening.
Thank you, Atul. Very nice talk.
Thank you.